Okay, let's talk a little bit about the relationship between delta G and the equilibrium constant. Delta G is the standard free energy change, where delta G standard for a reaction is the complete conversion of the reactants to the products. And delta G is the free interchange under non-standard conditions, the lack of the zero superscript. For example, concentrations other than 1 molar or pressures other than 1 atm will adjust temperature using our standard delta G equals delta H minus T delta S. But if there's anything else different, we're going to have to use this equation. Delta G is equal to delta G standard, which could include varying temperatures, plus RT ln of Q, where Q is the reaction quotient, R is the universal gas constant, 8.314 joules per Kelvin mole, but we'll have to convert that to kilojoules to match the kilojoules per mole that's typical on a delta G. So delta G's other than 25 can be calculated using delta G standard equals delta H standard minus T delta S. If it's at 25, you can use the tables in the back of the book, actually. At equilibrium, delta G is 0 and Q equals Kc. So we can derive a relationship where if we say, well, delta G is equal to delta G standard plus RT ln of K now, so we change the Q to K, the delta G standard, or the delta G is 0. We still got delta G standard, we still got plus RT ln of K now. And so then delta G standard is equal to negative RT ln of K. And you can use that to estimate the equilibrium constant under even non-standard conditions. And so that's called a thermodynamic equilibrium constant. It is a bit of an estimation. So then you can rearrange that and say K is equal to E, then that's each of the X, a mathematical function, not a variable, raised to the negative delta G divided by R and T. So let's look at an example of that. So we've got a K for our process, which is equal to 4.3 times 10 to the negative 13th. And we want to calculate delta G standard for the reaction if the temperature is 25 degrees Celsius, which is 298 Kelvin. We don't even really need to write the reaction. We've got everything we need for the formulas. So let's take a look at that. So looking at this problem, we know the equilibrium constant. We want to solve for the delta G. T is 298 Kelvin. R, remembers our universal gas constant, but we'll have to put it in kilojoules. So delta G standard is equal to negative 8.314 times 10 to the negative third kilojoules per Kelvin mole, 298 Kelvin. The natural log of our equilibrium constant, 4.3 times 10 to the negative 13th. Then you just have to run that through. And so we end up being able to estimate the delta G based on the equilibrium constant and vice versa. I'm running this through our calculator. And so delta G is a positive 70.5 kilojoules per mole, where the kelvins cancel. And would you expect that? Yeah, with this small of an equilibrium constant, I would expect delta G to in fact be positive. If I had a large, something with maybe even a positive exponent there, I would be expecting a negative delta G, because this indicates the reaction is reactant favored, so the reaction is not proceeding spontaneously. And so that's exactly what I would expect. So let's look at another problem. Let's say if we got a delta H standard of negative 20 kilojoules per mole and delta S standard negative 290 joules per mole Kelvin, we're going to calculate delta G and the equilibrium constant at 25 degrees Celsius. Now I don't have enough information to use the table, so I'm going to have to use the delta H and the delta S to get delta G. So let's do that. I've copied the information over. So delta G standard equals negative 20 kilojoules per mole. That's a favorable condition for spontaneity. Minus T, 298 Kelvin. And that's not a favorable condition because it's negative, but we're going to need to get that in kilojoules, so it'll match 0.290 kilojoules per mole per Kelvin mole. And then we're going to run that through our calculator. So we're going to say negative 20 minus 298 times a negative 0.290. So then we get a positive 66.4 kilojoules per mole. So in this case, the entropy dominates at room temperature, and we get a non-spontaneous process because I've got a non-spontaneous entropy. And so that we'd say this reaction at the current temperature is non-spontaneous. And so that's part of what we want right here. So we got a non-spontaneous entropy, or entropy, got a favorable enthalpy, but our Gibbs energy showing that the reaction overall is non-spontaneous. This is one that would occur more favorably at lower temperatures. That being said, let's calculate the equilibrium constant. E is equal to negative delta G, so negative 66.4 kilojoules per mole. And you got to convert it one way or another, so 8.314 times 10 to the negative third kilojoules per Kelvin mole times 298 Kelvin. Remember, all this here is in the exponent, even though I'm stacking a fraction and it might not look that way. So negative 66.4 divided by 8.314 times 10 to the negative third divided by 298. We're going to take that and raise it e raised to that power. And so you're going to get an equilibrium constant of 2.29 times 10 to the negative 12th. And that would definitely be a very reactant favored process, which would be about what we'd expect. Okay, let's look at one last problem. Let's look at this reaction where we got silicon dioxide reacting with carbon in the graphite form, plus chlorine gas producing silicon tetrachloride and carbon monoxide. We're going to determine if it's spontaneous at 200 degrees Celsius when there's 35.4 grams of carbon, 32.4 grams of silicon dioxide, 24.2 grams of silicon tetrachloride, and the partial pressure of the things in the gas phase is 0.25 atm for the chlorine and 0.5 for the carbon monoxide. Now, there's a couple of red herrings in this. We really don't care about the masses. what's going to affect the equilibrium constant, or the Q, is what's in the gas phase. And so we're going to focus on those two things in the gas phase, where our pressures are in ATM, where we get a KP or a QP if you want to do it based on gases. So let's look at the paper, but ultimately we're going to need a delta G for all of this. But really, just as I was saying, we're going to pretty much ignore those three things. We'll focus on these two once we get to that point. Before we get to that point, what I'm going to need is a delta H and a delta S so I can get the delta G standard. Which means we're going to be back to referring to our friend Appendix C, where we're going to need to pull the delta H and the delta S out of the table for each thing. And so we're going to, in fact, do that. So delta H standard is going to equal the products. So delta H standard for formation of our silicon tetrachloride in the liquid phase, plus 2 times the delta H standard formation for the carbon monoxide. That is our product side, and then minus the reactant side, heat of formation standard for the silicon dioxide, plus 2 times the standard heat of formation for carbon in the graphite form, plus 2 times the standard heat of formation for chlorine gas. We got a few elements present. So remember, delta H for free elements in their standard state is 0, so chlorine becomes 0. Now, what about carbon? Carbon is a little bit more interesting because there are several allotropes. And what we can see there, if we look, there's carbon gas, but there's carbon diamond, carbon graphite, and there's quite a few different allotropes of carbon, but the graphite one is the one where the heat of formation is 0. And so we have to keep ourselves aware of that. So so that will end up becoming 0, but it won't when we calculate the entropy. So the delta H for this particular reaction is going to be the silicon tetrachloride. And so that's going to be a negative 640.1 kilojoules per mole, plus 2 times carbon monoxide, a negative 110.5 kilojoules per mole. If you treat the coefficients as, or even implied ones as being moles, you can cancel the moles. And then the silicon dioxide is negative 910.9 kilojoules per mole, plus 2 times 0 plus 2 times 0, right? So, or you could just leave them off, right? There, because it's addition and subtraction, they're just going to go away. So then running all that through our calculator, delta H standard is a positive 49.8 kilojoules per mole. So that's an endothermic process. That's not favorable, but that's okay. We're not done calculating. Now we're going to do the same thing for the delta S standard, except we're going to substitute in the S instead of the H, but the functional form is identical. And then minus Now, the key difference in these two calculations is I have to look up values for everything because the entropy, or the S, is not zero for anything at room temperature. So let's look at the silicon tetrachloride. So we're going to look at that third column in the table now. So instead of focusing on delta H, which is here, we're going to focus on the S, which is here. In our case, 293.3. So, and they all tend to be positive numbers, 293.3, and they're joules per mole Kelvin plus 2 times the carbon monoxide value, 197.9 joules per mole Kelvin. That's my product side minus my reactant side, silicon dioxide, 41.84 joules per mole Kelvin, plus 2 times the carbon value. Remember, carbon is graphite, 5.69 joules per mole Kelvin. Notice entropy values for solids are significantly lower. And then 2 times entropy for chlorine. This is plain old chlorine gas. It's going to be 222.96 joules per mole Kelvin. So then we have to run all of that through our calculator. So let's go ahead and do that. And so we get a positive 190 joules per Kelvin mole. Now, we're still not done yet, but we did get a favorable condition for my entropy. So if the temperature is high enough, we could still be spontaneous. So now we want to get the delta G standard is equal to delta H standard minus T delta S standard. So then plugging in 49.8 kilojoules per mole minus, in our case, 473 Kelvin times, now I need to get that in kilojoules so I can match. So 0.190 kilojoules per Kelvin mole. That may very well be hot enough, but let's go ahead and check. 49.8 minus 473 times 0.190 and give us a negative -40.1 kilojoules per mole. So we would say that this reaction tends to be spontaneous. Under standard conditions. Non-standard temperature, but otherwise standard conditions. Now, if I want to get the delta G under these conditions, that is these pressure conditions, I'm going to have to use delta G equals delta G standard, which I just calculated, right, plus RT ln of Q. What's Q? Based on the equilibrium constant, but only of the gases, this one over this one. So delta G equals delta G standard plus RT ln of the partial pressure of carbon monoxide squared divided by the partial pressure of the Cl2 squared. Ignore everything else because they're solids and aren't going to participate in the equilibrium. But regardless, we need to plug and chug. Negative 40.1 kilojoules per mole plus 8.314 times 10 to the negative third kilojoules per Kelvin mole. Again, making the units match. Temperature 473 Kelvin. And then times Ln of 0.50 squared over 0.25 squared. We run that through our calculator and we will find our delta G under these non-standard conditions. And likely it'll still be spontaneous, but this number will vary just a little bit. So we're just taking a minute to run this through the calculator. Sometimes it's best to start from the logarithm function and work backwards because that's the more complicated function, but that's up to you. And really this section here is about 5.5, so it's not going to change this that much. And so we get a negative 34.6 kilojoules per mole. And so what we find is that this is the delta G under those non-standard pressure conditions. So it's not 1 atm, it's non-standard pressure conditions, but we can still say this reaction is spontaneous.